So hi, my name is Abiel. I'm the programming mentor at BOTBUSTERS. And basically this presentation is just like how to get from just a built robot into a robot that moves and that does something during a competition. So it's kind of like getting started. So here's a wiring diagram for the robot. It's kind of complicated, but the most important parts that we're gonna focus on for right now is just the robo reel, which is here in the right part, and the motor controllers. The rest we can just ignore. It doesn't really matter for what we're gonna do. So here's the simplified diagram. So basically we have the robo reel, which is kind of like a computer, which just sends the commands to the motor controller. The only thing they do is just they get a command from the robo reel and they move the motor. So it's super simplified, but it's basically what the robot can be distilled into. So we have three different types of chassis. I don't know how you say that in like plural, but you have tank chassis, I don't know, which are just like two sides. They have two motors on two sides and they move forwards and backwards. They're kind of like a car, I would say. You can't move them sideways. They're pretty good. They're pretty simple. So it's the most common one you'll see. There's also Mecanum, which it can move like sideways. They're okay. They're kind of slow at times and they don't have that much torque. And then there's Swerve, which is complicated, heavy, expensive, but it moves like whatever direction you want to give it to. So it's kind of cool. Each has its advantages and disadvantages. So it's up to more of the challenge and what your team can build to what you're gonna build. But for this presentation, the focus is tank, since it's the most common one and the most simple one to build. So there's also three programming languages which you can choose. Honestly, the two main ones in the competition is C++ and Java. LabVIEW is not that common right now, I think. I'm not sure. And honestly, if I were you, I would choose just the one that your team is most comfortable with. Honestly, LabVIEW isn't that good of an option since there's not that much documentation and support in general. So C++ and Java is just your best bet, I think. And well, after all that decision making and building the robot and everything, well, you want to make it move, right? So you start with the documentation, which is this really useful resource that you can get from FRC. They give us a library, which is called WPILIB, which basically implements a lot of really useful things that you can use to just like move the robot, make it autonomous and stuff like that. So you don't have to re-implement everything. So I think the most important part basically is just read the documentation. There's a lot of useful things there that you can use there to just make it work and just make it simple, easy, reliable. So as I said, we're going to start with a tank. So there's two sides. Let me draw here. There's just two sides, two motors, basically. It moves forwards, backwards. You can spin it around, etc. It's the most common chassis. So it's pretty simple to use. So you first off, you install the WPILib toolchain. I'm gonna just like gloss over this since most of it is like pretty well documented. Here's the links if you want to go and follow it step by step. But mostly just install it. Just go to the link. Just follow the tutorial. It's pretty step by step, pretty simple. And in the end, you'll get VS Code, which is just an IDE. It's just a text editor, basically, a fancy text editor, which you can use to just like edit your code and create your robot code and stuff like that. I mean, the most important part here is if you want to know more about like details or like step-by-step guide, just go to the link. This is also in the original documentation. Everything is there. It's very, very, very useful. So after you have your IDE, you can just create a robot code. And well, it's gonna be a little bit overwhelming, but we're gonna step by step it. So here you have basically an example code. This is just, I took it from the internet. I took it from the web page, just step by step. So first off, this is C++. Most teams use Java, but honestly, I don't know Java, so I chose C++ for this example, but they're pretty much the same. So first off, here we have two objects, the left motor for the robot and the right motor. They basically represent two motor controllers. So we tell them, okay, give me two motor controllers, one with the ID 0 and one with the ID 1. And we just get the motor controllers for that. That's it. That's basically it. And then afterwards, okay, here's the documentation for that too. Afterwards, we create, it's called a differential drive. So what this says is, okay, we have a tank chassis. It's just another way to call a tank chassis. So we give it the left motor and the right motor. That's basically it. So if we want to just like look into what each command does, we just go to the documentation again. So here's just a screenshot from the documentation. So basically what this says is to make a differential drive or to make like a tank controller, we give it the left motor and the right motor. So what we're doing here is we're giving it the left motor controller, which is this one on top here. Right here. And we're giving it the right motor. So that's basically it. Afterwards, I mean, we have like the robot drive object, which we can use for like other stuff during teleoperated or autonomous. Then we just create a controller. So what we're saying here is just create a controller. The ID is 0. So just the first controller that you find, and that's it. And then there's this function that's teleoperiodic. This is probably the most important part. So I don't know if you guys have used like Arduino or something like that, but basically what teleoperiodic is just a function that gets called over and over and over during teleop. So what you have to do is just make it so, okay, check the inputs and make the robot move. That's it. So here we have just a function that's called arcade drive from the tank controller. And what we give it is just two controller inputs here and here. There's other ways to do it. This is a pretty easy way. You just tell it, so, okay, give me input 0, which is just an axis on the controller, and give me input 1. So what that does, okay, so here we have, again, everything is just in the documentation. So if you don't know what something is, just look it up. It's pretty well documented. Everything is there. So it's pretty easy to just like figure it out if you don't know what you're looking at. So for example, here we have the documentation for arcade drive, where you give it the X speed and the C rotation. The last parameter is irrelevant for this example. So what you basically are doing here is you give it the X speed, which is the speed that the robot should move at, which is just forwards and backwards. It's -1 and 1, that's the limit. So what you give it here is just the controller input for the row axis 0. And you give it the C rotation, which is just the rotation for the robot. So you give this another controller. I think I'm going a little bit too fast. So if anybody has any questions, just feel free to stop me during the way. I think I can see them. So what we did here, we basically just took two axes of the controller, which is like any of these joysticks. And we made it so that the robot moves forwards and just rotates. So now we just have like a basic working teleoperated robot that we can take to competition. So this code, basically, if we want to see it in real life, well, first of all, we have to upload it to the RoboRio. So again, this is documented like step by step. So if you want to go to like the documentation, you just scan this code here. You can see like a step-by-step guide on how to upload it. But the gist of it is that you take your IDE, you upload it, it runs on the RoboRio. Okay, great. So how do I give it commands? So you use this thing called driver station, which is what we all use to control a robot. So you connect to the robot, you give it it's teleoperated by default. You just enable it, which makes it so it can move. And in the end, you get something that looks pretty much like this. which is just like a basic, simple teleoperated robot. It doesn't do anything else. It just moves around. And I mean, it's pretty cool because you can like build on top of that. So that's the basic building block of, well, everything. So what if we want to do something in autonomous? Okay, so there's same as the teloperiodic function, there's also the autonomous periodic function, which is basically just like a function that runs over and over and over again during autonomous. So here the important part is we have a timer object, which is basically just like, imagine the stopwatch on your phone. So first of all, at the beginning, you just start it. So it starts from 0. And then you're just checking if if 2 seconds haven't passed, just drive forwards. And if not, just stop. So basically what this is gonna do is just drive for 2 seconds and stop, that's it. So with that, you can just like get like a super basic autonomous going. That's really super useful for like most of the seasons. Because there's always like a challenge, which is just like move forwards. And it's pretty useful to just have it something super simple that you know that works. Okay, so we have something super simple. It moves, it goes forwards during autonomous, and that's pretty much it. So what if we wanted to do something? Okay, so I took it as an example. So this is Team Robonauts, which is a team in Houston, I think. They build, they call it the Everybot, which is just like a super simple robot that rookies can build with like off-the-shelf parts and just like stuff on the hardware store. So this is for the 2020 season. And I mean, the main focus is the intake mechanism, which is just the mechanism that picks up balls. So it's just a super simple mechanism. All it does is it has a motor, which spins this black part here. And it just deploys and retracts. That's it, just 2 motors. And with that, you can just score a lot of points and be very, very useful to like your alliance, because you can do stuff like pass balls to the other robots or just like deliver them to the loading station. I forgot the name, but you can just do lots of stuff with really, really simple things. Okay, so how do we control something like this? It's not that complicated. So we have 2 motors, which are this intake motor and this intake deploy motor. So this one, the intake motor, is just the motor that spins the, I don't know how you call it, but the intake itself. So it's the one that makes it so that the balls go up and towards the robot. So it's this one, the black part that spins. It's basically what does the most part. And then there's another one, which is just to deploy the motor, the intake, which is just the part that goes up and down. That's it. So adding on to what we had like previously in the teleoperated code, we just add functions to our teloperiodic part. Okay. So we have what we had already, which is this part on top. And we add this part, which is, you add a button to the control part. So here you have your controller and you tell it, get me a button. You basically just like say what ID the button is. I'm not sure which ID is what button, but you can just like check that out of like trial and error. It depends on your controller really. So what this does is it just returns a true and false for what you control for your button. So if it's pressed, it's true. If it's false, it's not pressed. So you just check, you get the current button state and you check, okay, if it's pressed, what should I do? So we just turn on the motor, the intake motor, which is the one that makes the balls go into the robot, and we deploy it. We just set it to like a velocity and we just make it go down, and we make it so it keeps going down all the time. And if it's not pressed, if the button is not pressed, okay, we just turn off the motor that spins, the one that picks up the balls, because we we don't really need it when it's retracted. And we just like do the same thing as the deploy motor, where we set it in reverse. So what this does is just it returns the intake mechanism. So in the end, so for example, here just it's when the button is pressed, you get the joystick control, and you can press the button to just lower the intake, spin the, I mean, I don't know what you call it, the rollers, I guess. And when you just release the button, in a second here, the intake goes up and the motor stops. So this is just like a super simple implementation. You can use it for other things. So for example, if you had just like, for example, the climber, which is this mechanism here, in reality, it's just a motor that moves, when it rotates in one direction, it moves up, and when it rotates in another direction, it moves down. So what you could do, for example, in a super simple implementation, is do something like really similar to this, where you just take another button and you make it so it sets to like one direction, and when it sets to another direction, it just goes down. So here you can just like make it move up, so it deploys, and you make it move down, so it climbs. So you can do like lots of stuff with super simple logic, like super simple controls. So I think the most important part here is just keep it simple. Simple works, and simple, I mean, it's reliable, honestly. So what are some next steps from here? So, okay, I think I went a little bit too fast. So if there's any questions, or if anybody didn't understand any part of what I said, feel free to ask them. So any questions? I'm just gonna pause here for a little bit for any questions. Okay, so I think the notification pops up if I do get a question, so it's okay. So what are some next steps? So here we have just a super simple implementation. Basically, it just moves, it does teleoperated, and it does it well. You can do decent job. I mean, you can do decently in a regional with this. So, okay, what's next? So there's a lot of things that you can do afterwards. A lot. It can seem a little bit overwhelming at first, but I think the main point here is everything is somebody already did it for you, and that's a good thing, because when somebody, like for example in WPILIB, you know that the code works, and you know that it is tested, and that other teams use it. So if in a regional, like you have troubles doing something, or if something doesn't work, you can just go up to another team and be like, hey, how did you make, I don't know, how did you do autonomous or something like that? And like most teams use WPILib, which you can also use. So it's pretty cool that, I mean, we all have like a common library. Also, if you need help during a regional, you can also go to like a CSA, and like honestly, they could help you out if you use WPILib, but not so much if you use your own custom library, which implements everything else. So from the things that WPILib gives you, I think that these three are like kind of important, but there's a lot of other things. So here we have, let me just draw. Here we have what is pretty useful debugging tool. It's called a shuffleboard. So what this does is, the image is kind of small, but what you have is you like publish like variables or numbers, strings, whatever you want to here. And this allows you to like modify like what the robot will do, or you can see what the robot is doing in real time. So this is super useful all the time, honestly. When you're testing, when you just want to know like what's my robot doing? Why is it not working? So I think like one recommendation is just like put everything on the shuffleboard. Just do it. It's worth it, honestly. So during debugging, it's like super useful. You can just like chart stuff. You can give it values. You could do anything you want. And during regionals, it's also super useful. Because like, what if you're on the field, for example, and I don't know, the robot stops working. It just stops, I guess. With a shuffleboard, what you can do is just like, okay, what is it doing? Why is it doing that? If you just like publish all the variables that you're using. So for example, if we wanted to use the shuffleboard in our example, in the previous example. So what we could be publishing is like, okay, what are the joysticks doing, for example? And what is the intake motors doing? So with this, we just know like, okay, so another example. So what if during a like testing, we find that, okay, so our enable intake isn't working. So first off, you check, okay, so am I sending the correct variable? Is enable intake actually changing? So you check the shuffleboard and you see, okay, yeah, it's changing. So that's a good thing. So afterwards, you say just like, okay, what are my motors doing? And you can go back to your shuffleboard and just like look at what the values are. So it's a really, 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 I can't stress this enough, a really useful debugging tool just for everything, honestly. And it's also pretty cool just to see all the data in real time. And again, if you want to just like see how it actually works and how you actually use it, it's pretty simple. But here's the QR codes for the documentation. Again, this is the same web page as in the beginning. Everything is there, everything. So yeah, it's pretty useful. So also a next step is PID controllers, which is just a completely, I mean, it's pretty intimidating at first, but it's super, super, super useful. I can't stress this enough. It's the most useful tool you're gonna have in FIRST and in robotics in general. So without getting into the math part, you don't really need to. You just need to read the documentation. So without getting into the specifics, what this allows you to do is, for example, you have, let's say, I don't know, you have just like your climber mechanism. So right now, what we're doing is called open loop control. We don't know what the robot is doing. We can see it, but the robot itself doesn't know where it's at. It doesn't know where the intake is, it doesn't know what it's doing. So what we can do is we put a sensor on it, which is called an encoder. So what this tells us is the position and the velocity of the motor. So what this allows us to do is control for position or for velocity. So for example, in the original example, if we want to control the climber in a more, I don't know, controlled way, we can say, okay, move to 1 meter. So the climber automatically moves to 1 meter and it stays there. Honestly, that's the most important part. It stays there. And if you try to push it down, it's gonna fight against you. So if we wanted to implement it for the EveryBot, so the original example, what we could do is implement a PID loop for the intake deploy mechanism. Because right now what we're doing is we were just setting it to a value and we're keeping it there. So what this is doing is just like the motor is going to move, it's going to keep moving always. So this is like pretty draining on the battery, pretty draining on the mechanism, because you're always going to be like crushing against the motor, let's say, or just like over torquing it. So what you can do with your PID loop is just say, okay, I want the motor to go at this angle, which is the deploy angle. So it moves and it stops when it gets there. That's the important part. It stops. So you can just use it for a lot of stuff. Or for example, if you want to retract it, okay, go to 90 degrees. So it moves and it stops. And if something like bumps against it or something, the motor just fights back. So that way you can just like control your mechanisms more and just know what the robot is doing. So PID controllers are basically a way just to like make the robot smart in a way. So you can do a lot of stuff. Honestly, everything is just built upon PID controllers. Autonomous, teleoperated, everything has a PID controller in it. It's just all of that. It just allows you to do so much more with your robot. So for example, if you have a shooter mechanism, so if you're gonna shoot balls, you put an encoder on it and you know what the velocity the shooter is going at. So with this, you can control the velocity that the shooter is going at. So with PID, what you can say, okay, at this distance, I need this velocity. So you can set that velocity and you can make it so it's reliable, which is like super important. And if you want to connect everything up, you can make it so that the PID just sends data to the shuffleboard. So it's really useful just for debugging too. So when you're tuning it, when you're doing everything, again, the specifics, you can read the docs for this. It's super useful to just debug everything. So another next step, okay, we have our autonomous right now. What does it do? Okay, it just moves 2 seconds and it stops. Nothing else, it doesn't do anything fancy, it doesn't just, no, nothing. So what we could do here is we could add encoders to a robot. So what this allows us to do is we can know where the robot is on the field. So it's really useful. It's super useful. It's without it, we can't do autonomous. So right now, for example, okay, 2 seconds have passed, we stop the motors. But what if during those 2 seconds, you don't cross the line that you're supposed to cross? You want to know where the robot is at, so you know when to stop the motors. So with the encoders, you can just like know the position of the robot and just check it and see if you need to stop or if you need to keep going. So you can use a PID controller again and just make it move to the position that you want. It's a little bit more complicated, but it's already implemented in WPI. So there's already documentation for that, and there's more specifics. Probably they're going to cover it in another conference, so I won't go that much into it. But you can just make it so that the robot does whatever you want it to do with PID controllers, encoders, and all the goodies like that. And really, I mean, honestly, software is free. You don't have to need to like have all the fancy mechanisms and fancy machining and everything to just do a go to autonomous. Software is free. Software is always going to be free, and it's always going to be like something that you can build with little resources, because there's already libraries out there that do it for you and that help you out for everything. So if I was starting a team, I think the one tip that I would give is just like focus on the software too. Because like what I see is that a lot of teams just don't focus on that, and it's just always like a last minute part, like, oh, we're gonna do this before the regional. But no, it's like a super important thing that wins regionals sometimes, because like sometimes the autonomous part is the one that gives you the most points. Like sometimes, okay, our alliance captain just like chooses based on what we see on autonomous, for example, because there's been like challenges where the autonomous just like wins the game basically sometimes. So one advice that I would give is just like focus on the code from the beginning and just don't ignore it, and just keep it like maintained and just like useful. So with all this, I mean, the most important part for autonomous is trajectories, which I won't get into that much. If you want to read the documentation, it's here. But basically, it ties into what I was saying before, is it's just a way to make it so that the robot moves how you want it to move during autonomous. So I think many of you have already seen like autonomous, where the robot starts here and I don't know, does this, goes grabs some balls and then shoots, does something like that. How do you tell that to the robot? I mean, you can't just say like, okay, go here. It doesn't work like that. So what trajectories are, it's just like a way to define a path that the robot can take to do something. So with all these tools, if you take it all together and you just like test it, testing is super important too. If you test it and just work on it, you can build something that's pretty good, and that's gonna work, and that's gonna do autonomous, and it's super good. It's super useful too. So with all this, I mean, all these tools applied into a robot, what you can do is a lot of like much more complex things. So for example, here's like a little video demo. So everything that you see on this robot is PID loops. So the shooter is a PID loop. the trajectories, PID. So everything is built upon like super simple things and super fundamental building blocks that you can just build upon and add complexity to. So for example, it's just following a trajectory. Like for example, this one. I mean, it's not this one, but we use the same tool, which is in WPILIB. So it just follows a trajectory and that's it. I mean, it's pretty simple stuff that works, and I mean, it gives you a lot of points. And same here. I mean, the shooter is just a PID loop running the velocity PID loop. It's nothing fancy. It's just something that's super simple. And when you build it all together, you get up with like a fully working autonomous that does something good or that works well. So for example, here's just like a lot of trajectories just like put together during like a lot of testing and just working it all out. And in the end, you just get a lot of like good code, I guess, good autonomous. So all of this we built upon these three main tools, I guess. So the trajectories, which just tell how the robot moves, the PID controllers, which control the robot per se, and well, the shuffleboard, I guess, just to see what the robot is doing for us humans. So with all this, I can't stress this enough. First gives you all the tools and all the libraries and all the building blocks. You just need to put them together. And they're all free. It's the most amazing part because it's a lot of work that people have put in to make it so that it's easy, it's simple, and it's tested. So I think if you're gonna take something from this presentation, it's just use WPILib. Use it, read it, study it, I guess. It's super useful. And you can build a lot of stuff with that. And other recommendations, I mean, as I said this enough, and I can't stress this enough, use the docs, read it. It's also in Spanish if you want. I think the translation is like almost 100% complete. I don't know, I'm not sure, but use it, read it, study it, I guess. It's super useful. Another recommendation is use things like GitHub or GitLab or whatever you want for your team. So what I've seen in other teams is that, okay, so there's just like one programming member team and he's the one that has the code and it's on his computer, so don't touch it and don't do anything to it. So what GitHub allows you to do is just like you upload all of your code, it stays there, and like other team members can just download it or whatever. But I think it's kind of like a Google Drive for code. You can collaborate, you can like do a lot of stuff. Honestly, I didn't put the link here, but there's a lot of good tutorials for how to use Git or GitHub, and it's super useful. So, I mean, it also helps if, I don't know, your laptop dies, you have a backup of the code. So it's super useful for that. You also have like a history of all the changes that you made to the code. So if you're testing one day and you're like, okay, I don't know, my mechanism works. And on the next day you make a change and I don't know, it stops working. You can just like go back and look at the differences between yesterday and today. And you can see, okay, so this is why it's not working. So it's super useful because it keeps like a history of everything. So in BOTBUSTERS, what we have here, we have like a code base. We release it yearly, basically. But we have a code base built from 2018, I think. And this is all on GitHub if you want to see it. We're going to release it pretty soon too. But the important part is that we have all of the history. So all of it, from going back to like 2018, when we first started it, to like yesterday. So it's super useful. Because for example, in 2018, it was a season where you had to use like an elevator. So we just built upon the code that we already did on like the previous season for like 2019 or 2020. So it's really useful to just like have that continuous history with the code, just keep developing it and keep improving it, and just applying all of the knowledge that your team has like gained with testing and just like experience on the next robot. And I think a very important part here is just ask for help. I mean, there's a lot of teams out there. We've all gone through like the same troubles, like the same problems. There's a lot of like helpful people out there. So if there's anything that you need help with, I mean, you can always post like Chief Delphi, which is a forum for FIRST, or you can post to like, I don't know, there's a Discord too for support. I didn't put the link here, but if you Google it, you probably can find it. So there's like a Discord with like super helpful people that will just like walk you through the problem. Or like during a regional, just like ask for help. There's a lot of people that can help you, and you would be surprised at how helpful they are and how like friendly they are. So I think like one of the most important parts is ask for help. We've all been through like the same things, and we all use basically the same code base, which is WPILIB. So we can all help you with whatever you want. So if you do this, and if you build upon what other people have done and what FIRST gives you, you can do some like stuff, like really complicated stuff with simple building blocks that people have already done for you. So for example, I mean, okay, I don't have the video here, but back in like 2017, there was no like WPILib wasn't what it was today. So there was no like paths and there was no like PID controllers, I think. I'm not sure about that part, but it wasn't that built. So like if you wanted to use paths or like do like a complicated autonomous, you had to do it all by yourself. So it was like a hassle. But now there's everything out there. There's documentation, there's videos even. There's code examples. Like for example, the original teleoperated example, it's just an example that I took from WPILib. There's everything out there. Everything is just documented, pictures, videos, whatever you want. Someone has already done it for you, and someone has just like put up a guide. So just Google it, research. It's the most important part. And with that, I mean, you can just like build a pretty complicated robot with a limited amount of resources, because code is free. I mean, all you need to do is just test it, and testing is free too. So if there's like a recommendation that I would give, is just like test your code, do things that people have already done, because like it's already tested. So WPILib, and don't try to like build the wheel. Just use what's already there, because it's super helpful. And well, I think that's about it. If you need like any help, you can always like go ask, I don't know, your local team, I guess, or the team that you know, like some guy or whatever. You can always ask us, for example. We have like an Instagram page, so you can always like DM us and be like, hey, we're having this issue and we can help you out. And if none of that works, or if you're just shy, whatever, you can always go to like other like web pages for FIRST. Chief Delphi is like the main one. It's basically, I don't know if you like guys have like used a forum, but you basically do like a post, like, okay, for example, here's like a guy asking for help for like electrical stuff, or like for technical stuff, or like just showing off the robots. Everything is there, like sort drive, okay, diagnosing an issue. Everybody's just like super helpful, and like, don't be shy, ask for help. That's one of the most important parts for FIRST, and there's a lot of helpful people out there. So I think that's pretty much it, kind of. This was more of like crash course, just for you guys to see what's out there and what you can do. Because honestly, the hardest part is knowing where to start, and the rest is just like research and just like testing and development. So it seems pretty intimidating at the beginning, but there's a lot of like good guides and good step-by-step tutorials on how to build like an autonomous, for example, which I think there's a presentation on that tomorrow, or I don't know when. Anyways, so you can always like look it up and just research. And I think that's pretty much it for this presentation. I went a little bit fast, but as I said, it's more of a crash course for what's out there and what you can do, and not a step-by-step tutorial. So I don't know if there's any questions. I mean, I'm pretty free to just like any questions about our robots, or like how did we implement this thing, or like whatever. I'm here to answer any questions that you might have.
Thank you, Ariel, for your presentation. I have here some questions.
Okay.
How much time does our programming team need to finish the code?
So, I mean, it depends on what you want to do. So you can have just like a basic working code in a day, I guess, if you know what you're doing. But when you want to test it and when you just want to perfect it, it's just like the time it takes just like really like goes exponentially, I guess. So what I would recommend is get started before the season, because there's a lot of things that you know that you're going to have to do. I mean, you know that you're going to have to build a robot, for example. You know that it's going to have to move, and that it's going to have to do something in autonomous. So one tip that I would give, the time that you get during the season to test the code and to like have like a physical robot isn't enough. So like try to work before that. Just try to like use all the time that you have, all of it, all the year. Just use it, because it's never enough and you're always going to need more time. So just try to like use the time that you have for everything. I don't know if there's any more questions.
I have another from an anonymous attendee. Is it important to have a laptop exclusively for programming or for the competition?
It's not. I mean, I would recommend having just like a laptop for the driver station, which is the one that you bring into the field and you control the robot with. It's not required, but I strongly recommend doing that because it gets speed up. You want it to just like run and you want it to work, because you don't want to be like fiddling with your computer during like a competition. So I would just recommend like getting semi-old laptop, not too old, just for the driver station. And for programming, you can just use your laptop. It doesn't really matter. School computers work fine too. So just use what you have.
An anonymous attendee asks, is it good to base yourself on the codes of other teams?
Yeah, I mean, I think most of the knowledge is pretty like, you gain a lot of knowledge from reading what other people do and what other people do. So for example, if like during a regional, you just like see like, oh, whoa, I wonder how that robot does its autonomous. Go up and ask. Like a lot of people are just like happy to talk about what the robot does. And I think it's super helpful. Most of like what all of FRC does is just like, okay, one team did it, we're gonna do it now. So like a lot of knowledge is shared and we can grow as a community, just like by sharing knowledge and by learning of what each other does that way.
Also, they ask if you have any teams that you recommend us to start following regarding programming.
So I think not really, honestly. I can't give like a good answer for this, but just look at what teams do. Some teams do like something like that's super complicated. Like for example, like Cheesy Puffs does like super like complicated code. I wouldn't recommend just like looking at their code, honestly, because it's like super complicated. It also depends on what you want to do. Like if you have like a tank chassis, look at what other teams with like a tank chassis do. So I think my main point is just like, look at what an average team does, because there's always going to be like a team that just like re-implements everything and that builds their own library and that does everything by themselves. And honestly, it's when you're getting started, it's not a good idea. But just like look at what they do, look at how they do it, kind of, and just try to implement that in the most simplest way. Because like a lot of teams just like overcomplicate the solution to the problem.
Another question is it okay to try to fix stuff that are a mechanical issue with programming?
So it really depends. So for example, if it's something that's super broken, like, I don't know, a motor, I mean, you can't fix that with programming. But if it's, for example, if you have like an arm on your robot and you find that it's just like dropping a little bit too much, you can just like fix that with PIDs, for example. So I would say it's more of like a case by case basis. But honestly, if the robot is simple, like if it's built in a simple way, if it does things in like an efficient, elegant way, the programming is just much easier and it just tends to work better. I mean, you can have like a complicated robot which does everything with PID loops and whatever, but honestly, simpler is better. Simpler is always gonna work faster and better, and it's just gonna like save you a lot of time. So try to like get the mechanical parts just like working really well so that your code doesn't have to just like deal with all of the issues that regard like mechanical parts.
Also, they ask which programming language is better to program and in which there are more resources.
So honestly, C++ and Java is your best bet. I wouldn't recommend LabVIEW because, I mean, at the beginning, it can look like simpler because it's more graphical. But honestly, there's not that much resources. And once you try to do more complicated stuff, it starts to get super, super complicated. So C++ or Java? Which one? I don't know. It's pretty much the same. I would just say like, what if like your mentor has more experience in Java? Use Java then. Or what if your mentor has more experience in C? Use C++ then. It really depends on what your team like already knows and what you feel more comfortable with. I don't think there's like the best language for FRC, but there's pretty much it's C++ or Java.
Okay, another sort of related question is which like mechanism or programming code do you like shouldn't use because it's too complex?
So, I mean, I don't think there's anything like too complicated. There's always like, it's always gonna end up being a good solution to the problem. But I think the main part is like try to keep it as simple as possible. So for example, like what happened in our team. So during 2018, we had like an intake, which just was kind of like an arm that went up and down. And we used like 2 motors for that. And it was just like a struggle because then it gets stuck and the motors burn out, or like you had to maintain the gearboxes, or you have to like change the PID loops. And like in off season, we're just like, why did we do that? Why didn't we just use a piston, which is like 10 times simpler? It works. It's just on and off. So I think what I'm trying to get at is just like, don't overcomplicate your solution. Just like try to think what's the simplest, most efficient solution, because you end up saving like weight, like development time. So I think there's nothing like you shouldn't implement, but I think there's always going to be like a simpler solution to like a complex problem.
Another question is, it is okay to make different autonomous for different roles in a match, or should they focus on a specific task?
I think it's always good if you have like different autonomous, if you have the time for that. I mean, if you can test them all and if you know that all of them work, go for it. I mean, there's always going to be like someone in your alliance that's like, okay, I only do this autonomous. And so like having another option is super helpful. So what I would recommend is if you implement, I don't know, like an autonomous that shoots balls, I guess, always have like the second option, which is just like move forwards. Because like in that way, if you have another robot that does more points during their autonomous, you can just like change it to like the move forwards autonomous, so that you do points and they do points and you end up like both of you winning. So try to do more than one. It's not super essential, but it's super useful in an alliance. And yeah.
Another anonymous question is how can you make that the mechanical and the programming areas are really closely intertwined?
So I think it's really important to have like a feedback loop into like what mechanical part is doing and what programming is doing. So here in the background, I have the mechanical mentor here. So what we do is we just like talk like, okay, for example, let's say we're implementing like an elevator. Okay, so how's it gonna work? What's gonna like the things that it's gonna have to do? And like I tell him like, hey, you're probably not using like enough motors for that, or hey, you probably should like implement a sensor for that. So it's like super important because like programming without the mechanical part is nothing, and the mechanical part without programming is nothing. So you should like really like communicate and just like build upon what each other is doing.
Well, this question is related to a question that I asked you before. Do you know any team that has a good documentation for programming?
I'm not sure actually. I mean, I've seen teams that implement their like own wiki pages and everything, but honestly, I mean, I would recommend just going for what FRC gives you and like WPILIB and stuff like that. And it's pretty much like the gold standard for documentation.
Another question, how much the teams has to improve the programming area year by year?
So there's always like room for improvement, honestly. Like every year after a season, what we do in our team is we meet together and we just like brainstorm new ideas, or like, okay, so this didn't work out during the season, what can we do to make it work? So there's always going to be something that needs to be improved. And what my recommendation is just like build upon what you already have, but try to implement new stuff during the way. So I think like one of like the most important parts in programming is like the path following algorithm. So start off with like super simple stuff, and like during the years, just like try to perfect it for what your chassis does and like what you want to do, and just like keep working on it and keep improving what needs to be improved.
Another question is, how much time do you think that it's correct to dedicate exclusively for the programming of the robot?
I don't, well, so here what we do is we work on like the building the robot and programming the robot at the same time. So the end goal is that when mechanical part is done, the programming part is also done. So we can get to testing like instantly, or just like debugging the code instantly. So I think in an ideal world, the programming is never going to take extra time to what the building the robot takes. I mean, it always does take more time, but I personally, I always try to like make sure that the program is ready before the robot is built. So that way there's no like empty space in between where it's just like testing for programming. Like, I mean, developing the code, but there's always going to be like testing time, which is honestly the most important resource in FRC, because everything boils down to like testing and drivers and autonomous and everything like that. It just works. You build upon that in testing. So try to like make it so that you have the most testing time as possible.
Okay, another question is, do you think that you should always rely on the autonomous to win?
I mean, you shouldn't rely on it, but it's really, really important too. Autonomous wins matches sometimes. I mean, if you don't do anything during teleoperated, you're obviously going to lose. So focus, first of all, get the teleoperated part working well and working like super good, because it's like for alliance selection, for example, if you see a robot that does really well in teleoperated, you're going to choose that robot even if it doesn't do anything in autonomous, because in the end you can just like make it drive straight, and that's an autonomous. So get the simple parts working first, like teleoperated, and score points for your alliance, and then work on the autonomous, is what I would say to that question.
And I think this is the last question. How precise does the trajectories have to be?
So that mostly depends on how much you want them to be and how much you need them to be. So if, like, for example, in the demo back there, since it was going just like at full speed, it wasn't that precise, but we didn't need it to be precise. We just needed it to pick up the balls, and that's it. So in the end, we just like fixed the not precise part with vision, and that's really helpful. But it depends mostly on what you want to do and what you need to do. So you're never gonna get it so like it's always like lands on the same spot and like centimeters of error. It's impossible, and it's not even worth the time. So it depends on the challenge and what you're trying to do, how precise you need it to be. Because if you want it to be more precise, you're gonna have to do it slower, and you don't really want to like slow down your autonomous when there's like only 15 seconds to do what you want to do.
Okay. Another question is, what area do you think that should take charge of electronics? Or is there like an area that is specific for this job?
So honestly, that's more of like based on what your team wants to do and like how many people you have on your team. So what we do here, for example, not saying that you should do it in your team, but what we do here is our mechanics people just like CAD the electronics part into the robot. So we just like assemble the electronics part, and we have like an electronics team which is in charge of like wiring up the robot and just like looking at the CAD and being like, okay, yeah, it's gonna work out, or no, you can't place the Roborio in that place, for example. So it's mostly on a team by team basis. If you have like a super small team, I mean, it's okay if your programming guy does the electronics part. Or if you have like a larger team, yeah, sure, have like an electronics team for the robot.
And lastly, I don't know if you have any advice for rookie teams or also veteran teams that you recommend for
So
this season.
I think the advice I would give is just like look at what's already out there and read what's out there. As I've said it, just like keep it simple. Just try to do like the most simple thing that works well and build upon like WPILIB. Like it's like super simple building blocks that you can use and that you know that work. So it's just like build upon what other teams have done, what WPI gives you, and just like keep it simple, keep it nice, keep it efficient, and also like practice. Because like sometimes like, okay, if you have like one day to like finish up your robot and you're like testing in your lab and you're like, okay, it works well. But there's a lot of issues that show up in practice and that won't show up in just like testing like 15 minutes. So practice makes perfect, honestly. Also for your drivers, for like mechanisms, you always like spot like issues after like certain amount of practice. So practice is like one of like the most important things in first.